Today we're going to be talking about the chain rule. The chain rule is super important to everything that we're going to be doing, and it's super important when we're taking derivatives of compositions of functions. So if you see here, if we want to find the derivative right now, what you guys would probably do is you would multiply out this polynomial. When you multiply out that polynomial, this is what you get. We know how to multiply out polynomials, so I'm not going to go through that with you guys. So now if I wanted to take the derivative of that, we would take the derivative the way that we have gotten used to taking the derivative. The hard part is actually doing that multiplying. That's going to take us a little bit of time, and to save time in the video, I didn't go through that. So this is what our derivative would be. But there's actually an easier way. So if we wanted to find the derivative now of this function to the 100th power, I don't want to have to multiply all this out to the 100th power. We're going to have some where we're not going to be able to multiply it out. But this is actually a composition of two functions, f of g of x. The outside function is something to the 100th power. The inside function is x squared plus 1. So then we take the derivative of each one of those with respect to x. Okay, now this is the key part. We're going to essentially be doing a u substitution. And you're going to get so used to this that you're not going to have to do this u substitution. But it's key when we're first learning it. So we have this original equation. If we let u equal x squared plus 1, so therefore y is going to equal u to the 100th power. So now we're going to take the derivative of that with respect to u. So u is our variable, so we have 100 u to the 99th. And then we're going to take x squared plus 1 and take the derivative of this expression with respect to x, so that's going to be 2x. So now what we're going to do is to find dy dx, we're going to take dy du and multiply that by du dx, canceling essentially out the du's to get dy over dx. So notice what happens when we do that. Dy du is 100 u to the 99th. Du dx is 2x. But what was u? U was x squared plus 1. So now if I substitute in, we have so think about what this is. Let's look at this. This first part here is the derivative of the outside function, leaving the inside piece, the inside function, just as is. And then this 2x, well, that is the derivative of this inside function. So there's a shorter way, our chain rule. So our chain rule, if f is a differentiable function at any point, what we can do, and it's a composition, is, this is the key part down here. I think about it like this. So you take the derivative of the outside function, leaving the inside function intact, and then you multiply that times the derivative of the inside function. Now looking at this function, the one that we originally started with, an easier way to do that. The outside function is something squared. So the derivative of that function of something squared would be 2 times that something to the first power. Well, that something is 4x squared minus 3x plus 2. Now we take the inside function and we have to take the derivative of that. So that's going to be, the derivative of that would be 8x minus 3. Now if you go through and you multiply this together, and I encourage you to do that, if you multiply that together, you end up with the same thing that I got on the first slide. So this is a lot shorter than what we would do on that first slide. Take the derivative of the outside function, multiply it by the derivative of the inside function. Our next example. This one has a few things built in. We have a product of one function times the other function, but then also notice inside that cosine is a composition of 2x. So we have a product rule and a chain rule. So dy dx, the derivative of y with respect to x, is equal to, okay, derivative of the first. Leaving the second function alone, I don't take any derivatives, plus, leaving the first alone, derivative of the second. So the outside function here is cosine. So the derivative of cosine is a negative sine of the function inside. So negative sign I'm going to take and erase my plus sign and make it a negative. But I also have to take the derivative of the 2x because that's a composition inside our cosine function. So therefore then our derivative of 2x is just 2. So simplifying that, we get 6x times the cosine of 2x minus 6x squared sine of 2x. Our next example. I would recommend we rewrite this as x to the third plus the cosecant of x to the 1/2 power. So now when I find dy dx, we have the whole outside function of something to the 1/2 power. The derivative of that would be 1/2 times that something, reduce your exponent by 1, that something, the inside function stays the same. Now we take the derivative of the inside function. The derivative of that inside function is 3x squared minus cosecant cotangent. I don't worry about that 1/2. We've already incorporated the 1/2 in the very beginning. So now simplifying. This blue part, well, that has a positive exponent, so that goes on the numerator. And then on the denominator, we have the negative exponent part and the 1/2. And we can leave it like that. It's okay in calculus to have radicals in the denominator now. Okay, this function. Make your life easy. I have a philosophy that I stole from a coworker of mine at a previous school where I always say work smarter, not harder. If you manipulate this equation into the polynomial on the bottom to the negative 1 power, we don't have to worry about our quotient rule. But we have to remember our chain rule. So the derivative of this, we bring down the exponent, subtract 1 from the exponent, and then now multiply by the derivative of the inside function, so then simplify by making this negative 3x squared minus 2. I distributed the negative to the polynomial that's going to be on the top. And then this bottom piece is going to go on the bottom. You don't need to worry about squaring out the bottom. I'm okay if you don't square that up. Now one that's a little bit more complicated. So we have here the sine of 1 plus cosine of x to the 1/2 power. When I'm finding dy dx, or y prime, I think about it as layers of the onion. Okay, what's the outermost layer? The outermost layer is the red piece. So the derivative of sine is the cosine, and leave everything inside intact. Now we multiply by the derivative of the next function. Now what's the next function? The next function is actually this whole 1 plus cosine to the 1/2 power. So I have 1/2 times, leaving the innermost function intact, to the negative 1/2 power. Now lastly, we have the 1 plus cosine, or the green piece. The derivative of that, derivative of 1 is 0, derivative of cosine is negative sine of x. Simplifying that, the cosine to the square root of 1 plus cosine of x, that's in the numerator, along with the negative sine of x. Now the 1/2, the 2 goes in the denominator, along with that 1 plus cosine of x to the 1/2 power. And you can make that radical if you wanted. I just chose to leave it as a fractional exponent.
Okay, in this example, we have a lot of chain rules going on. Okay, first we have the function of something to the 6th power. Then inside that function, we have the sine with a bunch of stuff going on. And then we have the tangent with another function inside. And our last function is the 6x cubed minus 5x plus 8. So remember, you work from the outside in. So taking the derivative, finding dy dx, the derivative of y with respect to x. First, the outside function, the red function, bring down the 6. And then everything inside stays the same. And here it's just a bunch of writing. Now remember, reduce your power by 1. Now the derivative of the sine. Derivative of the sine is the cosine. And again, everything else inside stays the same. Now we take the derivative of the tangent. Derivative of the tangent is, now you'd multiply, but I've ran out of room, so I'm sorry, the derivative of tangent is the secant squared of the 6x cubed minus 5x plus 8. And then you have to take the derivative of the 6x cubed minus 5x plus 8. You don't have to worry about taking the derivative of secant squared. Okay, you're just looking at this original function and keep working through your layers of your onion inside. So the derivative of that would be 18x minus 5. And then you are done. And hopefully that color coding helped you guys see where you're taking your derivatives.
Okay, object moves along the x-axis so that its position is given by the position function. Find the velocity. Remember, the derivative of position is equal to our velocity function. Derivative of that. Derivative, you have the sine, and then you have a function inside, that 5t minus 3, that's a function inside. So the derivative of sine is the cosine of 5t minus 3. I don't take the derivative of the 5t minus 3 when I'm writing out the derivative of sine. I then take it separately, and the derivative of 5t is 5. So really that would be 5 cosine of 5t minus 3. Okay, find the slope of the line tangent to the curve at pi over 6. Remember, when you see something to the 4th power there, that really means that. So y prime would be 4 times the cosine of x to the 3rd power. That's a derivative of the outside. Now derivative of the inside is the negative sine of x. Okay, so now I evaluate the function. The negative I'm going to put with the 4. Cosine of pi over 6 to the 3rd times by the sine of pi over 6. Cosine of pi over 6, root 3 over 2. Sine of pi over 6 is 1/2. Negative 4, 3 root 3 over 8 times by 1/2. That's going to simplify to negative 3 root 3 all over 16. Oh, I'm sorry, all over 4. 8 times 2 is 16. I forgot to multiply by the 4 on top, so that becomes a 4 on the bottom.
This next example is one you're going to find a lot of on the AP and on my quizzes and tests. So we have a chart of values, and we have to evaluate the derivative with respect to x for each one of the following combinations of x. So here we have a composition of functions. So I want you to show me the derivative. F prime of g of x, the derivative of the outside function, times by the derivative of the inside function. Okay, now g of 1. Go to g of x column, the 1 row, that's 2. So we're looking for f prime of 2 times by g prime of 1. Now, f prime of 2. F prime column of 2 is equal to 6 times by g prime. Now, g prime column of 1 is equal to 9. So we get the final answer of 54. And that is it for today. Please make sure your lesson questions are submitted on time.